Now let's consider the entropy change due to heating. As we heat a substance up, the molecules move faster, and therefore the substance becomes more random, and the entropy increases. So you remember your heating equation from last semester. Q is equal to mc delta T, and you remember this product, mass times specific heat. So this is grams for the mass. The specific heat is joules per gram degrees centigrade. So we can have also different units for the constant C. We can have it in joules per mole per Kelvin, and this is called the heat capacity. So if these units are joules per mole Kelvin, this is the heat capacity. So the specific heat has units of grams and degrees centigrade. The heat capacity has units of moles Kelvin. So we're going to use the heat capacity for the entropy of heating. So in this case, Q would be the heat capacity times delta T, and then we'd have the number of moles multiplied here. So we can, if we want to just do it on a per mole basis, write Q is equal to C delta T. We got this from the change in the heat is equal to C dt. So from our entropy expression, now the entropy change is equal to dq over T, so we can put C dt in for dq. And then we can integrate both sides of the equation. And let's say we do it under constant pressure. So this will be heat capacity at constant pressure. So integrating the left side will give me delta S. The right side, and heat capacity is a constant, we'll assume. So this will give me this equation. So under conditions of constant pressure, the change in entropy due to heating, and this is the higher temperature and lower temperature, or T2 and T1. So the entropy due to heating is just the heat capacity at constant pressure times the natural log of the temperature 2 divided by temperature 1. We can also do this for constant volume heating, and we will have an analogous equation that will be delta S is equal to CV, natural log of T2 over T1. So if we heat at constant volume, this would be the entropy change, and this is the final and initial temperature. So this is the equation to use for the entropy due to heating a substance. So it's different because CP and CV are different. So we'll have a different value if we do it at constant pressure or at constant volume. Now, why do we have a difference? Why is entropy different if we do it under conditions of constant pressure and constant volume? Say we have a container and we have a gas, and this container is rigid. Say it's a steel container, and we add heat to the gas. So heat flows in, the gas is going to warm up, the molecules are going to move faster, it becomes more random, the entropy increases, and the pressure increases in the gas. Now say we have a balloon, and we allow heat to flow into the gas. So now, since the balloon is not rigid like a steel container, the balloon can expand as the pressure of the gas increases. So if you remember, when a gas expands, it cools. And so we start heating the gas, it expands, it does work moving the air out of the way as the balloon expands. So it takes more heat to get to the same temperature change, because some of the heat is heating the gas, some of the heat's being lost as work as the container expands. So we have to add a little bit more heat under constant pressure to have the same temperature change as we do under constant volume. So the entropy change at constant pressure will be greater than the entropy change at constant volume, because we had to add more heat at constant pressure to get the same temperature change, since some of the heat went to expanding the gas.